Hi, and welcome to Hyperbolic Trigonometric Functions. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. Chapter 5, Logarithmic, Exponential, and Other Transcendental Functions. Should give it a proper title it deserves. Comes to us from Larson's 11th edition calculus text. We call it section 5.8 here at UTEP, but it's actually 5.9 in the new edition of the book. So what are hyperbolic trig functions? We know that we can define the 6 regular trig functions from the unit circle given by x squared plus y squared equals 1. Well, the 6 hyperbolic trig functions come from the unit hyperbola, and the only difference is that now we're subtracting, so it's x squared minus y squared equals 1. If we were to solve for y in both cases, we would have these graphs. So the unit circle we're used to, there's the top half of the unit circle, didn't feel like doing the whole thing, and the top half of the graph of the unit parabola. So now we're defining our values based on this red line. So here's the definitions of the hyperbolic functions. Hyperbolic sine of x, and we'll frequently call this sinh of x, is e to the x minus e to the negative x over 2. And if you've been following my calculus series, because you're probably one of my calculus students, we had this as a derivative. We looked at this in derivatives of natural exponential functions. Cosh of x is e to the x plus e to the negative x over 2. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine. And the others are defined similarly. Reciprocal functions, just like before, sine, hyperbolic sine, and hyperbolic cosecant are reciprocals. Hyperbolic cosine, hyperbolic secant, reciprocals. Hyperbolic tangent, hyperbolic cotangent, reciprocals, and hyperbolic tangent and hyperbolic cotangent can both be defined as quotient identities. So very similar, just don't forget to type the H. The H distinguishes hyperbolic trig functions from the regular trigonometric functions. We have hyperbolic identities, just like we have regular trig identities. Cosh squared minus sinh squared equals 1. Subtraction, right? That comes from the unit hyperbola that we talked about in the earlier part of the lecture. Now, so these are corresponding to our Pythagorean identities in regular trigonometry. Hyperbolic tangent squared plus hyperbolic secant squared equals 1. Hyperbolic cotangent squared minus hyperbolic cosecant squared equals 1. And we can solve for some square formulas, right, using double angles. Pause if you want to write these down. We do have double angle formulas for hyperbolic sine and hyperbolic cosine. We have sum and difference formulas for hyperbolic sine and hyperbolic cosine. Notice that sum and difference formulas for regular trig functions and the hyperbolic trig functions, cosine stick together for the hyperbolic cosine sum or difference, and for sine they mix it up, sines and cosines. But this is calculus. So let's talk about the derivatives and integrals of hyperbolic functions. Let u be a differentiable function of x. Then, and we can prove these using our definitions, the hyperbolic sine being defined as e to the x minus e to the negative x over 2. If we were to find the derivative, we would find that that is the derivative of the inside, so derivative of u, times hyperbolic cosine of u. The derivative of hyperbolic cosine is also just the hyperbolic sine. Notice no negatives here. The derivative of hyperbolic tangent is u prime secant, hyperbolic secant squared of u. Man, that is a mouthful. So these are very similar in terms of the functions. The only difference, the positive and negative signs. Sine, cosine, and tangent, whether they're hyperbolic or not, I consider to be the big three. Hyperbolic sine, hyperbolic cosine, and hyperbolic tangent all have positive derivatives. Whereas the secondary three, Hyperbolic cotangent has a derivative that's negative, hyperbolic secant has a derivative that's negative, and hyperbolic cosecant has a derivative that's negative. But notice the derivative of secant is still secant tangent. The derivative of cosecant, still cosecant cotangent, and so on. So the signs are what changes. We also have formulas for integrals of the hyperbolic functions. The integral of the hyperbolic sine is hyperbolic cosine plus c, and vice versa, integral of hyperbolic cosine of u du is hyperbolic sine of u plus c. So we're just going backwards on the rules that we just had for our derivatives. The integrals of hyperbolic sine, cosine, and a resulting hyperbolic tangent, those will all be positive, and the other three will be negative. Let's use some of these. So if I want to find the derivative of f of x equals cosh of x minus 2, I know the derivative of cosine, hyperbolic cosine, is hyperbolic sine. Leave the inside alone, multiply by the derivative of the inside, but the derivative of x minus 2 is just 1, so there we are. The derivative of hyperbolic tangent is hyperbolic secant squared. Don't forget to type the h. Students are always writing back to me, hey, I forgot the h, that's it. Don't forget the h. H matters, it's hyperbolic. Leave the inside alone, 3x squared minus 1, times the derivative of the inside being 6x. And I write the 6x in front so it doesn't somehow sneak inside my hyperbolic secant squared. To find the derivative of g of x equals x hyperbolic cosine of x minus hyperbolic sine of x, I'll use the product rule. And my product rule, here, I'll take a first derivative of the second, so derivative of hyperbolic cosine is hyperbolic sine, plus second times the derivative of the first, hyperbolic cosine of x times 1, and then the derivative, minus, the derivative of hyperbolic sine is hyperbolic cosine. These two cancel out. I didn't simplify my answer whatsoever. Look at all this room on the page, and I just forgot to keep typing. This is hyperbolic sine of x times x. As these two, one's positive, one's negative, they're the same value, they'll cancel out. Attention to detail, and I slacked right there. But I did remember the h. Let's look at some integrals. The integral of the hyperbolic cosine of the square root of x all over the square root of x. At first I'm thinking, well, the integral of hyperbolic cosine is easy because that's hyperbolic sine, but I got to deal with these square roots. So let's let u be the inside of the trig function, that's square root of x. And then the derivative is 1 over 2 square root of x dx. I don't have an extra 2 hanging out, so I can multiply both sides by 2. 2 du is 1 over the square root of x dx. Now let's rewrite our integral as the integral of hyperbolic cosine of x times 1 over the square root of x dx. A great mathematician's trick, instead of dividing, we multiply by the reciprocal. That way we can see it all separated. This 1 over square root of x dx is going to be replaced by the 2 du. Hyperbolic cosine of u. And now we have 2 hyperbolic sine of u plus c, and we reverse our substitution. If we start with substitution, we have to use it a second time. A second time here is at the end. If it was at a definite integral, the second time to do the substitution would be in changing our limits of integration. The integral of hyperbolic secant squared of 2x minus 1. I'll let u be the inside, 2x minus 1. Then du is 2 dx. I don't have an extra 2 hanging out, so 1/2 du equals dx. I can now rewrite my integral as 1/2 the integral of hyperbolic secant squared of u du. I know this integral is hyperbolic tangent of u, still have my 1/2 on the outside, plus c. Replace my u, and I'll have 1/2 hyperbolic tangent of 2x minus 1 plus a constant. So we keep going. Integral of hyperbolic cosine of x over the square root of 9 minus hyperbolic sine of x squared dx. keep rolling here. I'm going to let u be 9 minus hyperbolic secant squared of x. Then the derivative is minus 2, and then I have to use the chain rule. Minus 2 hyperbolic sine of x times hyperbolic cosine of x dx. And I'm cool with that hyperbolic cosine of x dx, but I don't have an extra sinh in here anywhere. Nowhere. So that's not going to work. This is not a straight up u substitution. What does that mean? That means it's a good thing I was just recording the inverse trig function lectures today, because I recognize the form as an inverse, an arc sine function. Oh man. So if a equals 3, then a squared is 9. A little brain hesitation there. We'll let u be the hyperbolic sine of x, and then we have a squared minus u squared. Also, to find du is hyperbolic cosine of x dx. Look at that, being a slacker again. Bad notation. Bad professor. So, I could take my integral. I replace hyperbolic cosine of x dx with du. I rewrite my radicand as 9 minus u squared. I know this is the inverse sine of u over a plus c. The inverse sine of the hyperbolic sine of x all over 3 plus c. So yeah, don't just go straight up substitution. Sometimes that doesn't help. And a lot of times I don't like writing things in these lectures that are not helpful. But it's good for you to see that even if you try something and fail, it's alright, because you can go back and try something else. You have a lot of skills at your disposal at this level, so keep trying something. We do have inverse hyperbolic functions. Those look like fun, don't they? This is a set of identities you should just know. Just write them down, take a screenshot, do something. We have differentiation involving inverse hyperbolic functions. Wow, notice it's only the big 3. And then the other 3. Oh my goodness. But that looks familiar. They look familiar. There's subtraction going on here. There's some addition going on here. But they're very similar to the ones that we had before for just inverse trig functions without the hyperbolic. We also have 3 antiderivatives. So we have our forms, depending on whether it's addition or subtraction here. We'll have addition or subtraction here. Similarly, addition or subtraction stays constant there. More examples could be had, but these are formulas. You need to be able to fit the form, match the formula, and then make sure you get all your absolute values and radicals and plus or minus signs right, and you'll be just fine. Never forget the constant of integration, c. That's it for this lecture on hyperbolic trigonometric functions. Thanks for listening.